In this example, we're going to work through a problem using an equilibrium approach in which we have a beam with a distributed load. Now, the distributed load that we have in this case is a varying load. Okay, at the minimum, we have 4 pounds per inch. Up here at the maximum, we have a weight of 12 pounds per inch. We have a beam, in this case, it's 20 inches long. And what we're trying to do in this example is solve for the reactions. Now, this particular example illustrates the fact that we have a cantilever beam. All right, so we essentially have 3 reactions at this wall. We have a reaction in the X, the Y, and then of course we have a moment resistance. This end of the beam is completely unsupported. Okay, so the first thing we're going to do is we're going to take this distributed load and we're going to break it up into some different shapes. So, by the way, the approach that I'm using is called Composite Shapes. And I'm going to take this load that looks like a trapezoid and I'm going to break it up into a rectangle, okay, which has an intensity of 4 pounds per inch. Okay. Then I'm going to break it up and then I'm going to add a triangle, okay, where this value here is 8 pounds per inch. Okay, so again, the overall was 12 pounds per inch on this end, so I'm just breaking it up into a rectangle and a triangle. And what I'm going to do is I'm going to solve for the force that each one of these distributed loads, I'm going to solve for the force that each distributed load can be represented as. It basically is a concentrated force. So I'm going to call this one force 1. And this one, for lack of a better term, I'm just going to call force 2. So the idea is I'm going to take this distributed load and I'm going to represent them, each one, as a single force. Okay. Force 1 is just going to be the magnitude of force 1 is just going to be the area of this rectangle. So we have 4 pounds per inch on the y-axis, and then we have 20 inches on the x. So this would give us a total force of 80 pounds. Likewise, for force 2, I'm going to be solving this area of a triangle. So here we have 1/2. My base again is going to be 20 inches. And the height in this case would be the 8 pounds per inch. Okay, so I have 1/2 of 20, which is 10 times 8. So this is also 80 pounds. So now what I'm going to do is I'm going to take this free body diagram and kind of redraw it over here. All right. Let me go ahead. I'm drawing my reactions. What I'm solving for, as I mentioned earlier in this problem, is the reaction in the Y, the reaction in the X, and this moment. And this point here is point B. I should have written that here. This is point B. So that's why I'm using B with subscripts X, Y, and then for the moment at point B. Okay. Now it's good that we represented each one of these distributed loads as a single force. Of course, we need to know where that force is going to be at. So for the centroid of a rectangle, in this case we have a rectangle that's 20 inches long. The centroid will occur at 10. So this force that we had right here of 80 pounds is 10 inches from the left. Okay, and I'm just going to use the dimension from the left. Now for a triangle, we have to think to ourselves, okay, if we have a triangle, where's the centroid of a triangle located at? So I'm going to kind of sketch it over here. Okay, we know that for a triangle, the centroid is located at 2/3 whatever this base is. Okay, so in our case, it would be 2/3 of 20 inches. Okay, so that's the total distance from this point here to the centroid where this force is acting. It's going to be 40 over 3, which should be, let's see, about 13.3 inches. So F2, which we determined earlier was 80 pounds, is at a total distance of 13.33 inches. So that means this dimension here is 3.33 inches, which leaves me with this last dimension here of 6.67 inches, right? So I've got 10, 3.33, 6.67, all that equals 20. Okay. So at this stage, I've got it cleaned up. Again, this is also a free body diagram. Really important. The only other thing I'm going to include with my free body diagram, and this is just what I always do, is I just mention what my reference axes are. So x is positive going to the right, y is positive going up, and a counterclockwise moment is positive. Okay. So now what I'm going to do is apply equilibrium. I've got essentially three equations I can use. Some of the forces in the x, some of the forces in the y, and moments. So I'm going to go after the low-hanging fruit first and do summation of the forces in the x direction. Okay. So when I look at my free body diagram, the only force I have is Bx. So Bx must be equal to 0 if all the forces in the x direction have to balance out to 0. Okay. Why don't we take a look at forces in the y? Okay. In the y, I've got, again, based on my positive notation, I have minus 80 from force 1. I have another minus 80 from force 2. Okay, then I have by going up, which would be positive, and all that has to be equal to 0. So that gives me a value of by. When I solve this, you'd have a minus 160 that we move over. So we have 160, and these were in pounds. Yep. So there's Bx. I'll go ahead and box this. I'm sorry, By and Bx. And then the last thing I need to solve for, of course, is that moment. For this, I'm going to take a moment about this point B. So the moment, again, at any point along that beam also has to equal 0 if the whole thing's in equilibrium. And so in this case, I've got, let's see, I'm going to go ahead and have F2 at 6.67. Now F2, this is going to be a clockwise moment. Okay, so that's positive. So I've got 80 pounds at a distance from point B of 6.67 inches. Okay. Likewise, I have F1, and that also is going to be a positive moment relative to B because it's going counterclockwise. Okay. And that's at a distance of 10 inches. Okay. All that's resisted by this moment that we have at point B, right here at that point. Okay. I have no other vertical forces that would cause motion or rotation, so our equation is now equal to 0. So again, this is from force 1, this is from force 2, and this is my moment. Okay. So when I solve this, I get that the moment about point B comes out to be 1333.6 pound-inches. Okay. And it's in the direction that I have shown. Because based on the way I was showing it, right, it was going counterclockwise, which is why I have the negative here. And so if I move, for example, if I move this term over here, then you have all this as positive. So it is in the direction as we had indicated on the free body diagram. Okay, and that concludes this example of applying equilibrium approach to a distributed load on a beam.